Right. I'm now looking at the spring potential energy is for light springs. In fact, it is massless, not useless. Actually, it is less mass. It's very wrong to use massless. So we will take no mass is possessed by the spring, but I have attached a mass of a Kaplan to the spring. Now this is the natural length. Now if I take it, I elongate it. Elongate. Elongate by how much? Let me say I have done by E. Elongation is E. Right. Okay. Now, if I generally do it by X, what is the spring force? Force is like this, your displacement, these two are opposite, Right. So, minus of minus kx dx. Force is, spring force is kx minus, I have taken that, otherwise you take kx dot dx, cos 180 minus sign, you can have it. So you get k into x squared by 2, x1, 2, x2. Now this is valid whether it is elongation or whether it is compression. Now this is very important. The work done, I will give you here, you have to be very, very sure of this. Work done in the case of spring. During elongation or compression, as long as I am elongating it, work done by spring is negative. As long as I am compressing it, force is like this, displacement is opposite. The work done is negative. So here also negative. Both the cases it is negative. This is first point. From state of elongation to natural length, in the process of state of elongation or compression, remember. Now here suppose I am leaving it, it will come like this, displacement is like this, force is like this, so the work done in which case is positive. Similarly, this is compression. From compression to this is the force, this is the displacement, therefore positive. Now this is very, very crucial. You have to understand this. Okay? So during the process of elongation or compression, work done by spring is negative, and during the process of either elongation or compression to the natural position, the work done is positive. That's what you have to keep in mind. Remember, if it is conservative force, partly you have to have positive, partly you have to have negative. The displacement is 0, you are supposed to get it to 0 likewise. Okay? So let us see now. This is work done. What about the potential energy? Whether this is in a state of elongation, state of compression, P is stored always. How much? It all depends on this is interesting, you see. Potential energy. If you take it as work done, will be what? Minus half K into x2 square minus x1 square. So work done is like this and the potential energy is like this. Now one important thing is, you see, half kx square, I can write it as fx by 2, f is kx. If I am taking it from 1 to 2, see f2 x2 minus f1 x1 by 2. Okay? This is another way to give work done or the potential energy expression in the case of spring. One, of course, is this, or k into x2 square minus x1 square. Fine. Now, f is kx or x is f by k. If I substitute it, f squared by k squared, what do you get? F squared by 2k. In which case, how do I write the expression? One, two, three, x1 to x2, you can use it in this way. Then, if I take this is how you are doing it, okay? Kx dx and otherwise you are doing it as f dx. If f is linear, I can take average f to outside and integral dx, or I write average. So you have f1 plus f2 by 2 is average and integral dx is x. So you have x2 minus x1. This is another form of your potential energy or work done. f1 plus f2 by 2. If you want, you can expand this, and this is valid only when f is equal to kx. Wherever force is linearly related with the displacement. So there are 4 ways of writing expression for the spring potential energy in this case. With the fx you can do, fk you can do, kx you can do, fx you can do in different ways. Right? In this, if you want to prove, I will write it. Look, f1 x2 minus f1 x1 plus f2 x2 minus f2 x1 by 2. But f1 x2, what is f1? kx1 x2. And what is f2 x1? kx2 x1. You see, these two terms cancel. That leaves with the expression. Only to confuse people, they try to ask in this way. This is valid only for, I repeat and reiterate, this is valid for any time force is proportional to the displacement. This is valid, okay? Now, as far as the spring is concerned, you can say, as far as the spring is concerned, suppose this is in an elongated state. Yeah, this is brought to this V, and if you leave it, it may come to get compression. Okay? See. If ideal, no friction at all, and there is elongation and C, same. from this to this, there is no change in potential energy. That is very important in the case of spring. Whether it is in a state of compression, whether it is in a state of elongation, it is not going to have any difference as far as potential energy is concerned. Okay? That is about the spring potential energy and work done by spring. Now, work done by centripetal force. It could be anything. Work done by centripetal force. Gravity, spring, electrostatic, combination of that. And in this, its work done by is always zero. Why? Force is like this, displacement is like this. Angle between them is 90 degrees. Therefore, work done by centripetal force is always zero. Then work done by friction. Now, important. Work done by friction. For example, this is a horizontal surface, you have normal force. I am using a force F. This is Fk. What is Fk? Work done by friction. Displacement is like this, force is like this. So, Fk dot dx. Fk dx cos 180. Cos 180 is minus 1. What is Fk? Mu k n dx. What is n? mg dx. Is all work done by friction. So you have x so if you take from 0 to, then x will become 0, it becomes minus p mgx. Is this okay? Now, if mu itself is equal to bx, mu varies with the surface, with x, it increases. In which case, what is work done by friction? Integral minus mu k is bx, n is mg dx, that is minus bmg. X dx is x square by 2. Maybe 0 to x you can take. So you have minus bmg x square by 2. Now if you wish p, you can write it as mu by x. No problem, whichever way you want you can do. This is the work done by friction. If I say what is the work done against friction, you have to give positive sign. Against friction means negative of that. Okay? This is work done by kinetic friction. Now this is not necessarily negative all the time. Be careful. Suppose if I ask you, what is the work done by static frictional force? Now you see, in this case, I am applying a force. This is Fs, this is N, this is mg. It is not moving. Therefore, work done by Fs is 0. Because there is no displacement. Okay? Fine. Now, if I take a body, applying a force F, this is body number 1, this is N1, this is move, there is friction there, it is Fs. Now I have moved this and this whole thing has come to this point. So this is the displacement of. Now this is M1, this is M2. So F minus Fs equal to M1 A1. On M2, what is on M2? It is going with A1 therefore. And this is because friction is taking it forward, therefore Fs is equal to M2 A1. Okay? Or F minus Fs is equal to M1. A1 means Fs by M2 or F is equal to Fs into or Fs. If M1 is M2, so you get. This is how you have to get your expression for static frictional force. This is not a standard expression. Every time there is a problem, you have to work out. Okay? Fine. Now, this frictional force is responsible for this displacement. Work done by static frictional force is Fs dot dx integral and Fs dx cos 0 or Fs is constant, Fsx, Fs is F M2 x by. This is very important, my dear friends. Positive. Previous case I have shown you that as 0. You get the point. This is very important. In the case of M1, now work done by Fs on M2 is this one. On M1, same displacement, but frictional force is opposite, therefore minus Fsx, Fm2 x by M1 plus M2. In this example of two body system, I am trying to give you that the static frictional force work done could be 0, could be positive, could be negative. This is very, very important. I want you to understand this. Same is the case with the kinetic frictional force. I will show you. Now, is this clear? Okay. Now, work done by kinetic frictional force. Let us say this is F. 1, 2. I am taking this to be smooth. This is slipping. Means what? This is how it is. Strictly speaking, this is the displacement. How does frictional force act on Fk? That is Fk. Forward displacement is this. So both are in the same direction. W is equal to mu n to gx. Positive. Work done by frictional kinetic frictional force can be positive, can be negative. Work done by static frictional force can be positive, can be negative. It is wrong to presume that all the time the kinetic frictional force will give negative work. No, no. Please be careful about this. I'm talking of on body M2. On body M1. Work done by kinetic frictional force is negative, and that is mu M2Gx. In the same case, you have got a positive work done and a negative work done. You have to be very, very careful in giving these kind of things. Okay? This is about the frictional force, work done by friction. So, what is work done by normal force? Now, this is crucial. Look, I am applying my force. This is N, this is Mg, and what is this? This is displaced, but work done by N is, N dot dx integral, and this is 0, because N is like this and G is like this. Does it mean that normal force never does work? That is wrong. I'll show you now. Suppose I have a body. Now this is mass M, and this is an elevator accelerating up. Okay? Now this is the normal force on this body. So after some time, maybe the body has gone here. So displacement is x. So work done by normal force is so N dx nx. Nx, N is nothing but, in this case, Mg. What is M? And you have to find out here. So N minus Mg. So in this case, N is so much. So M into, this is very important. In this case, work done by normal force is what? Work done by normal force is positive. Now, suppose if it is descending with the acceleration, so I have given positive descending with acceleration. I draw the diagram again for you. A is less than G. Otherwise the body will float. So N is like this, Mg is like this, A is like this. And let me tell you, this is your displacement. So N displacement are opposite. So minus Nx is the work. And what is N here? Mg minus N is equal to Mn. So answer is minus M into M into. This is the work done by normal force. A is less than G, so negative. The previous case, positive. And in other previous case, 0. So work done by normal force can be positive, negative, 0. Work done by kinetic friction force can be positive or negative. Work done by static frictional force can be positive, negative, 0. Work done by spring force can be all the three. Work done by gravity can be all the three. You get the point? Right. Okay. So I think we have almost worked on these concepts. Okay? Now with this background, let me put a stop to this here. And in my next class, I keep touching on combination of the forces and work done, work energy theorem. It will be very, very interesting, my dear friends. Thank you.